Good afternoon.
Good afternoon, Priya. Good afternoon, everyone.
Ma'am,
Good afternoon, ma'am. Good afternoon.
Yes, please.
can you make everyone attendees?
Okay, just a minute. Yeah, please wait. Yes, can you all attend as attendees? I have made some changes now. Are you able to see as attendees list?
We are still presenters.
I have made changes. Uh, So I have to make changes. People in my organization
You can
or
press. I think
yes, sorry.
that's the option was who can present, and you have to make it to only me. Who can present something like that?
Okay, now you are able to see. Refresh the page and see it. I have done it already. Can you check it?
Can you share your screen one?
No, attendees list. I'm talking about attendees list.
We are still presenters,
You're
ma'am.
still
Can you
presenters,
share?
ma'am. So can you share your screen so that we can
I
check it?
said only me. That's it. I said only me. Keep
For
refreshing.
which question? For which one, ma'am?
Who can present?
Okay.
I've already set it. Is it reflecting?
No, ma'am.
No? Okay, let me share the screen. Yeah, are you able to see the screen now?
Yes, ma'am.
This is the change I should make, right?
Yes, ma'am.
Have you saved it, ma'am?
Did it, they're doing
Now
it.
we are attendees, ma'am. Now we are attendees.
Okay. Okay, fine. Today I'm going to complete mathematical derivation of SVM and tomorrow principal component analysis and feature engineering on Monday. Okay, Monday, please let me know if you are free post lunch, that is after lunch time. Do you have any placement activities?
Ma'am, we have an elective class schedule.
Okay, when was it scheduled? At what time you have classes?
The
We are
elective
not.
is at 2:30.
Okay, fine. Then later next week, some other day, I will schedule the class. Monday, I and Priyanka both have examination duties. That is why we will not be able to take up. And Tuesday, no class. Wednesday, yeah, most probably. Let me know when you people are free in the afternoon, okay? So that I can compensate my classes. Okay. So the previous class you saw what is SVM hypothesis, what are class labels, optimization, SVM optimization. This is the final equation of SVM optimization. And this SVM optimization can be derived taking the parameters such as functional margin and geometric margin. You also saw functional margin, what are functional and geometric margins. And this is the functional geometric margin is what it is, just a it is an Euclidean distance between certain point x to the hyperplane. And what is functional margin? It says how confident the model is in while predicting the classification, while categorizing the groups into different classes. It represents the correctness and confidence of the prediction if the magnitude of the vector w raised to t orthogonal to the hyperplane. And this is the functional margin with respect to the training sample, ith sample. This is functional margin with respect to the entire data set. Geometric margin with respect to data sample I, geometric margin for the entire data set y. And next, deriving the optimization objective. Now this is the hyperplane. What is hyperplane and how it is derived? See, after discussing few things about SVM, we know that SVM goal is to maximize the geometric margin and it returns the corresponding hyperplane. Here we have linearly separable data sets. Here, since the data values are linearly separable, we can draw as many planes as possible. But here the thing is, it aims at maximizing the geometric margin. It means the width, the region width should be maximized in order to make correct classification. Okay, what it means that out of all possible planes, out of all possible planes, all possible hyperplanes, SVM chooses that hyperplane which has the maximum geometric margin. So in this case, we can see that the hyperplane which is in red color is the best separating hyperplane or the optimal hyperplane. Here the geometric margin is functional margin scaled by W. What is this W? W, it represents the optimal hyperplane. So it can be mathematically represented as W comma B. It is hyperplane equation. Argmax of W of transpose into X plus B, Y superscript I divided by modulus of W, subject to Yi W transpose T Xi plus B, which should be greater than or equal to Wt into W of transpose T into X plus B for all I, which can also be written as W of B, W comma B, argmax of Y. So what you can make out here, hyperplane with respect to each data sample I and the hyperplane with respect to the entire data set. This is the initial optimization problem. So now look at this diagram again. We are deriving further. So here we have positive classes and here we have negative classes. This is a positive hyperplane whose value is +1, and this is a negative hyperplane whose value is -1. So these are negative samples, these are positive samples, and this hyperplane is a positive. These are vectors, right? Support vectors. These 3 points are support vectors, and these 3 are support vectors. What are support vectors? The data points that are closest to the hyperplane, right? So now let us consider the 2 hyperplanes, that is positive hyperplane. The respective hyperplanes are positive hyperplane. This is denoted by phi of plus W transpose T into Xi plus B plus naught. B plus is equal to 0. This is a hyperplane passing through the positive vectors. And similarly, phi minus, it is hyperplane passing through the negative vectors. So W transpose T into X superscript I plus B subscript minus is equal to 0. That is, here we are representing positive and negative hyperplanes mathematically. So now optimization, how the optimization problem can be formulated. Here it can be formulated with this objective function. WB argmax is equal to, here we are trying to combine both the planes and substitute the parameters, and we get, after substituting, you try this substitution later, and the final derivation will be WB. It's a hyperplane which is equal to argmax B positive plane minus negative plane divided by modulus of W, and which gives argmax value as, this is the final value after derivation step by step. This is the final value, argmax of 2 divided by modulus of W. It means it is, why the value is 2? First, distance from the hyperplane to the positive margin here. This region, okay, this region plus the distance from here, distance from this hyperplane to the positive classes, and D2 is distance from hyperplane to the negative classes. That is why we are taking 2 divided by modulus of W, subject to Y superscript I W of T into S superscript of I plus B, which should be greater than or equal to 1. This is the optimization problem. But here what you can say, what can you observe? when you try to plot a graph, what do you observe? Just analyze what happens.
What exactly, ma'am?
Hello?
Like this is the what is it? 2 by W is the margin, no, ma'am.
Yes.
The length.
Yes.
So,
2 by
what
W
are you
is
asking?
you're taking here when you plot, what can you observe? When you plot a graph,
Ma'am, when you plot the graph,
or when you plot a graph, what can you observe? What type of curve do you get?
it's like one hyperplane is linear, no, ma'am. So, what we are getting, it's like the distance between support vectors, the
Okay.
2 by W,
Okay.
the margin.
Okay.
So, the
Here,
expression, the
yes. Wait. Yes, correct. You are correct. The parameters W and B in this optimization function should be that the functional margin should always become 1. Our aim is to make the functional margin as 1. So, which makes the objective function W and B is equal to R max of 2 divided by W. So, here W and B have been scaled such that the functional margin becomes 1. It has become 1. So now when you plot a graph, when you take any data set, take any complex data set and derive that optimization problem for taking these samples, you will get a non-convex function, right? So we know that by statistics, from statistics knowledge, we have to avoid this convex function. It is not preferred for data visualization or for classification. So since this is the non-convex function, this should be avoided and we should go for convex function. So try during the lab. Okay, take any data sample, categorize it, then try to derive the equation step by step following the same parameters equation and plot a diagram. You will get non-convex function. So this should be avoided. Okay, here it means in here actually it has reduced the optimization problem by reducing the number of computations that are to be performed. Here we tried substituting and finally we came up with the simplified solution, but the output is non-convex. So here it actually statistically speaking it should be avoided. So here what to do, how to overcome this. So instead of non-convex, we should go for convex function. Here how it is done, squaring the norm of this W, squaring the W value in the multiplicative inverse of object function. Okay, here squaring the W, squaring the norm W in the multiplicative inverse of objective function, it gives us convex function. So convex function, how does it look like? See here. Yes. If you take multiplicative inverse, square of multiplicative inverse, you will get argmin of W modulo W square divided by 2 subject to yi wt xi plus b, which should be greater than or equal to 1 for all I. So this is the optimal function, the final optimal function, which is a convex function. So this is the output. So what we are trying to do? We are trying to group a particular data samples. Okay, we are trying to categorize the data samples into particular groups. So here this is the objective function and it is preferred for the categorization. So maximizing the function f is same as minimizing the function g is equal to 1 by f. That is taking the that is squaring the normal w in the multiplicative inverse. We are taking the inverse and squaring it. They give maximizing the function, which is same as minimizing the function g is equal to 1 over f. They are inversely proportional to each other. So in simple terms or in normal terms, how this optimization can be written? Optimization can be written as if it is a positive plane, okay? If yi into w into x1 plus b is equal to 1, then xi, yi is support vectors, then save the parameters w and b. Else, if they fall in the negative samples, if the data belong to negative classes, then also save the parameters w and b. Else if this equation yi w dot xi plus b minus 1, if it is less than 0, if it is less than 0, then update the parameters. What we are doing here, we are here in this condition, we are trying to find if the data sample belong to positive group. Else, if data samples belong to negative group, then also in both the cases we have to save the parameters. Else, if this value y wx plus b is equal to 1, if this equation gives us minus 1, if this equation gives us less than 0, then we have to update the parameter. This is the algorithm for SVM for optimization. So next is kernel trick. I think we have discussed kernel trick in very short in the last class. Here what we can say, in the first one there is a clear separation of data classes. There is a line which clearly separates the data sets into two groups, and here the data samples are non-linear, data are jumbled. So here kernel trick, it addresses the problem of non-linearity. It means it bifurcates the mixed data, complex data into different groups. So what exactly we are doing? We are trying to move from two-dimensional to three-dimensional or two-dimensional to n-dimensional for better analysis and visualization of data. So here this is one dimension, two dimension, three dimension data. In one dimension, in zero dimension, no dimension at all, data is just, it is a data point. In one dimensional, it is a line. In two dimensional, the visualization is through a plane, and here it is through a three dimensional plane, planes and hyperplanes. Yes, kernel trick. What is kernel trick? It's a method of moving the data analysis step from two-dimensional to three-dimensional, so that it is curved in the higher dimensional place. When we go for kerneling, we go for kerneling in case of non-linear data sets. Here you can see data are not linearly separable. So what we do, we lift the, we add one more coordinate to this x and y axis, and to in order to separate the classes into, in order to separate the data into different classes, we are lifting these portions upwards. Okay, so this is a clearly convex function.
Excuse me, ma'am.
Yes.
Ma'am, you in the like couple of slides ago, you told that the functional margin should be greater than or equal to 1, no, ma'am? Like that's what we are trying to get.
Greater than or equal to 1, but that minimum condition is it should always be 1 or greater than or equal to 1. That is also case, but the nominal value of functional margin should be 1.
So how, from where is that derived, ma'am? Is there like part where, is there a reason for?
Here you have to, yes, here you have to do derivations. There is no clear derivation here, just I think here, yeah. What we have seen in the above steps in the previous slides, I have derived step by step. You have to substitute the values here in this. Just a minute, I'll show you.
Yes.
Yeah, from here. Keep on substituting the values. Okay, here, yes. Here and next. Yeah.
But this derivation is only for this one, the objective function, no, ma'am. This is just the
See, yes,
condition.
objective function, but functional margin, geometric margin, all they have to be derived in separate, because here if I include those, if I show those derivations in this, it takes more time. But if you want me to show how it is to be made one, then I can tell you in the next class. Okay, what exactly is your query?
Ma'am, like, why is it one? That was my query, ma'am. Like, why?
Yeah.
How did we arrive at it should be
See,
greater than or equal to one?
yes, yes. Why it is one means prediction for any prediction algorithm. If in general what we take, if algorithm is able to predict well, if any algorithm is able to make any correct predictions, we say that it is success. That is one. If it is not able to predict well, it is considered as less than 1. Okay, so that is why functional margin is some value actually. Okay, functional margin is a value which tells whether the algorithm is able to classify properly or not. So that is indicated through a value 1. If it is less than 0, it means it may be neutral or it may be not that effective. Is it clear?
Yes, ma'am. Yes.
Okay, thank you.
Ma'am,
Yes,
ma'am, if your slides, like after this, you have brief like what SVM says, like if yi into wx plus b minus 1 equals to 0. Can you just go to that slide once, ma'am?
here, this one,
Forward, forward. No, ma'am, the summarizing slide.
this one,
No, ma'am, the three conditions.
this one, this
Yes,
one.
yes, yes. Yes,
Yes,
ma'am. Generally, what we say is when we draw a plane, we say like, uh, 1 minute. So, the positive side will be like wx plus b greater than 1, no, ma'am.
correct.
And the negative side will be like less than minus 1. And the hyperplane, ideally, it will be like uh, uh, what wx plus b into y equals to 0, no, ma'am.
Correct, correct.
So when we
So in
try
this
for
case,
it,
yeah, tell me. Yeah,
so the first one, the positive one is covered in the first if condition, like the positive side of hyperplane.
yes.
If suppose class 1, say
Now
class 1
here,
is covered
instead
in
of
the.
taking is equal minus 1, you take it equal to 1. Okay.
Yes, ma'am, yes, ma'am. Then that
It
will
is
be
it
like
is written in the other way. That's it. It is simple. It is written what you are saying is correct. It is written in other way.
yes, ma'am, yes, ma'am. So generally equals to 0 is hyperplane, no, ma'am. So
Correct.
equals to 1 will be like class 1. And
Positive,
then
positive 1.
yeah, positive 1 or class 1, like
Minus
I
1 is
said.
negative 1.
Yes, ma'am. Yes, ma'am. Minus 1 is negative
Yeah, wait,
1.
I will
So
go to that
it
slide.
will.
Don't get confused. I will go to that slide. You remember only these values. Okay, I think yes, this condition. Okay, you can take
Yes.
these conditions. Hello?
Yes, ma'am. Yes, ma'am. Yes, ma'am. What the conditions I haven't written, ma'am. So what I'm saying is the three conditions are there, no, ma'am. So
Yeah,
the first positive case is covered in the first if class, and the
correct.
second one is like greater than 0, I guess. Like I don't remember it. I was confused analyzing it, so I didn't
Don't
note it
get
down.
confused. Don't get confused. It's simple here. If if this plane value is greater than or equal to 1, y is equal to plus 1, it means it is positive hyperplane. Okay, and if it is this, it's negative hyperplane. Here, positive hyperplane wx plus b is equal to minus 1. Here you can see it is below the hyperplane, right? So that is why h1 is negative. So here this hyperplane is above the this particular it is this plane belongs to positive classes. So this plane, this dotted plane belongs to positive classes. So how this h2 is denoted? H2 is denoted as wx plus b is equal to 1. So here the line, dotted line which falls above the hyperplane is denoted as positive. The dotted line which falls below the negative plane is denoted as negative. The same thing here. So what is your question? I also got confused.
So the first one is like the class positive class, no ma'am.
Correct.
The second one, the
Yeah.
second one can be the second one is possible in which class, ma'am? It this also falls in the class one, no ma'am. When this is possible, ma'am, yi into wx plus b. Suppose
Greater
if
than
we
or
take
equal to 0.
if we take the y into wx plus b is like 1 or greater, then it will be possible. If it is less than 1
Correct.
is automatically it will be less, no ma'am. So it will be like either
Correct.
hyperplane or negative class. So and
Yes.
the last one is like the negative class itself
Yes.
or the
So
hyperplane.
here you need to
So
say
what is
both
this
are
division,
positive
ma'am?
classes. Both belong to
Yes,
positive,
ma'am.
and this is
Both belong
negative.
negative or hyperplane. So what are we concluding it finally? What
Yes.
is this layman term SVM optimization? Like I could not conclude
Here
anything from.
Here, if it means from this we can conclude that there is a plane and all the positive samples, if this value is equal to 1, greater than or equal to 1. If the value is greater than or equal to 1, it means functional margin is 1 and it means the classes are positive. If the functional margin value 1 is less than 0, if it is less than 0, it means they belong to negative classes. You take this two. If this value is greater than or equal to 0, in that case values are positive, the samples are positive, the classification values are positive. If this is the condition, they belong to negative samples.
Ma'am, support vectors lie to the both of the sides, no ma'am.
Yes.
Support vectors. So
Yes.
the first case, am I audible, ma'am?
Yes. First case.
So the first case is like why it is written like the next y is support vectors, because it is not covering the left case, no ma'am. And what is meant by
No,
saying the parameter?
here X is the input sample, Y is the prediction. Okay, for ith data sample, for ith prediction, these are not input sample. One is the input variable, the
So
other one is output
ideal,
variable.
yes ma'am, yes ma'am.
Okay,
Oh, it's input only, no ma'am. X and y are in the graph, no ma'am.
yeah,
So support vectors lie in the both of the classes, in the positive class and in the negative class. So
okay,
ideally, this first condition should satisfy the support vectors equation. So for all the support vectors, suppose we have one support vector in class 1 and two support vectors in class 2. So
okay.
those three support vectors should be satisfying this equation. But then from what we have studied earlier, that equation and this equation is not matching, ma'am. So that's what I was asking.
Because here equations differ here. I am taking data from different sources. You should be able to correlate that. Okay. So here simple words. If these conditions, if these two conditions are greater than or equal to 0, what you have to do? You have to save the parameters. It means they belong to positive classes. If this value is less than 0, then they belong to negative classes and prediction is not correct for this particular classification. So this is the algorithm, or you just ignore it. Okay, you need not take this. This I copied from some other website. Just ignore it. Okay. Hello.
Yes, ma'am.
Yeah, consider the previous equations. And if you want more information about convex, non-convex function, you can go through website and work on it. Okay, kernel trick is that is shifting from two-dimensional to higher dimensional, three-dimensional or higher dimensional space, and so that it is curved in the higher dimensional space. That is, we mainly focus on convex functions. And here you can see that uh, this is the hyperplane, optimal hyperplane, and there are so many hyperplanes, but we have to draw an optimal hyperplane which maximizes the distance between the vectors. And this is the complex data and how it is visualized using PD. And what we are doing here, we are adding one more coordinate Z and to make this separation, and here we are able to group the samples into two sets. Kernel definition. Here in kernel method, the data set X, okay, this is the data set X, is represented by an n into n kernel matrix. Okay, here we take the matrix n into n. That matrix, it has pairwise similarity comparisons where the entries I and j, the entries I and j are defined by the kernel function, what we say, k xi and xj, okay, k of xi and xj. This kernel function has some mathematical property. This function acts as a modified, what do we say, dot product. Here basically it acts as a dot product matrix, and it takes as input its input vectors in the original space and returns the dot product of the vectors in the feature space, which is called kernel function. Formally, if we have data x and z which belongs to x, and there is a mapping, that is transformation from x to r to the power of n, then k of x z is equal to phi of x comma phi of z. It means we are going for transformation from 2D to 3D. This particular equation is called a kernel function. Here the kernel function, just a minute. Okay, here the kernel function accepts inputs in the original lower dimension space. What we are saying, we are moving from 2D to 3D. It takes the inputs, input values or independent inputs in the original lower dimension space and returns the dot product of the transformed vectors in the higher dimension space. Okay. So now, what can you understand here? What we say, if we have three samples, x, it takes x1, x2, x3, and y values y1, y2, y3. Here, this equation, kernel trick equation, it allows us to operate in the original feature space without computing the coordinates of data in higher dimensional space. If we take this x1 to x3 values transposed of this is t, it implies transpose values x1, x3, x2, x3, y1, y2, y3, and taking the phi of x, it gives us 9 possible computations transform value, and phi y, it also gives us 9 possible transform values. So if we multiply these two, phi of x3 and phi y, we get for I, j is equal to 1 to 3, xi, xj, yi, yj. So what do you understand by this? What is happening here? What are we trying to do? This is the kernel function, okay? This is the kernel function which is denoted as k of x comma y. So here we are going for some computational methods. We are using some computations. What if there are n number of variables, x1 to xn, y1 to yn? So there will be a lot of computational steps, and computation time is also more, which increases the time execution as well as it consumes lot of resources. So if we consider these three values, here what it does, we have to do computation in 9-dimensional space. Here we have 9 variables, here also we have 9 variables. Computation is done in 9-dimensional space, and we reach the same result within the 3-dimensional space by calculating the dot product of the x transpose and y. Okay, the computational complexity in this case is O of n, okay. So if we use kernel function, here what I'm trying to say, if there are more samples in X and Y set, it involves more of computations, which obviously increases the computational time, and it consumes a lot of resources. So instead of computing these large number of steps, we can go for kernel trick. So what this kernel trick does is, kernel trick it makes our work easy. So it is more efficient. It offers a more efficient and a very reasonable way to transform data into higher dimensions. Here the kernel function is applicable to SVM algorithm, and here we use for other image recognition algorithms these days. Say any computation involving the dot products, okay, any computations involving the dot products X and Y can utilize the kernel trick functions. So here kernel trick X transpose Y of square, which gives us X, for all I, J, 1 to 3, X1, Xj, Yi, Yj. So it is minimizing the computational complexity. Go through this. Kernel trick. It is used to convert the dot product of support vectors to the dot product of mapping functions. For I, alpha of I minus half for every I and j, alpha of I, alpha of j, yi, yj, and here support vector vi, x of svi and x of svj, and this is the SVM objective function. So here you have to replace the dot product of vectors with the dot product of matrix function. So you will get the final equation, SVM optimization objective with the kernel trick. This is the final function. See, students, you have to work on lot of mathematical steps. In statistics, statistics itself is a huge, it's a big ocean. So here we came across with different terms like functional margin, geometric margin, hypothesis, right? Different terms we are using. You have to search, you have to Google those concepts, you have to work on yourself to make those concepts clear, because we cannot teach all the things, and you also know it, you are also aware of it. You have studied those concepts in third semester, fourth semester of your program, BE program, right? So just to have a recap, you just go through the website and try to study those concepts, which will make these things easy to understand. Okay, there are kernel functions here. This is the equation, and these are there are kernel functions and different types. It can be represented as a dot matrix. It's a generalized one. This is a dot matrix, and it reduces the complexity of finding the mapping functions. And there are different types of kernel functions: polynomial kernel, Gaussian kernel, radial basis function kernel, and sigmoid kernel. Here you need not go more in detail about this. Types of functions are not required. If at all, if anybody is interested, you go for Gaussian kernel. RBF is not required, sigmoid is not required. First two, okay, first two are okay. Yes, kernel trick for nonlinear data. Okay. And here how the visualization is done, same thing. It is this kernel trick can be solved using Lagrangian formula, using Lagrangian multipliers. Okay, here you saw different diagrams. So kernel trick is basically a simple method where a non-linear data, mixed data, jumbled data, where a non-linear data is projected onto a higher dimension space in order to make it easy to classify the data where it could be linearly divided by the plane. Okay. Yes, mathematical representation of kernel trick. So again, same thing, positive hyperplane, negative hyperplane. Positive hyperplane is denoted as +1, negative hyperplane is represented as -1, and this is an optimal hyperplane. Value is 0. So the distance between h1 and h0, h1 and h0 is written as wx plus b, okay, divided by modulus of w is equal to 1 by modulus of w. So the total distance, double of this, that's it. The total distance between h1 and h2 is 2 into modulus 2 divided by modulus of w. And here our aim is to minimize this modulus of w. If there are no data points between h1 and h2, okay, when xi w plus b here, when xi into w plus b is greater than or equal to 1, when yi is equal to +1, xi into w plus b is less than or equal to 1, when yi is equal to -1. So if it is combined, you will get this equation yi into xi into w, which should be greater than or equal to 1. Next, Lagrangian formula or Lagrangian multipliers. Do you remember Lagrangian multipliers, Lagrangian formula?
And we haven't studied this now.
Lagrangian, third semester.
No, ma'am, we haven't done this.
Okay, then you please go through the website. Okay, or else you can speak to your teachers, or else, okay, this will also do little knowledge of Lagrangian, which I'm going to explain now. This will also do, okay. Here the basic idea of SVM and kernel trick is to find the plane which can separate or classify the data with maximum margin as possible, okay. The margin is also called the region, or it is also called street width. And here the distance you saw here, the distance between h0 and h1 is then this equation. So the total distance between h1 and h1 is the h1 and h2 is 2 divided by modulus of w. So in order to maximize the margin, okay, in order to maximize the margin, we need to maximize the modulus of w, okay, we need to maximize the modulus of w with the condition that there are no data points between h1 and h2, okay. So here what we can say, we can intuitively observe that we are trying to optimize the margin or the width by maximizing the distance between the support vectors, vectors. And an optimization problem. What is optimization problem? Optimization problem is basically of either maximizing or minimizing the real function by systematically choosing the input variables from the data set, okay, and computing the value of the function. Optimization means either minimizing or maximizing. And here we have to see that the support vectors should be away from the margin hyperplane, optimal hyperplane, and not on or in between the region. Hence, we can say that it is a typical constrained problem or optimization problem. So now here we have a Lagrangian equation, and this particular kernel trick can be mathematically solved using Lagrangian formula. Here first we'll find that the margin or the decision boundary for linearly separable data, okay, plane. Then we solve the Lagrangian equation for multipliers for multiple input variables. Yeah, and here the decision boundary or the hyperplane. Here names are interchangeably used. Decision boundary, street width, hyperplane is denoted as, all are same. Decision boundary, street width, hyperplane, all are same. And decision boundary or hyperplane must classify all the points correctly. Yi, W transpose T, Xi plus B should be greater than or equal to 1 for all I. This is the condition for ideal hyperplane. This is how the optimal hyperplane is denoted. And decision boundary can be found by solving the subsequent optimization problem. So here we have to minimize this subject to minimize half modulus of W square subject to Yi W of T, W transpose T, Xi plus B greater than or equal to 1 for all I. And here what you see, sorry, what you see next? And here so this is a constraint, okay? Here this is a constraint optimization problem, and solving this problem requires Lagrange's multipliers. So which is subject to this 1 minus yi w of t xi, same thing for all, for I is equal to 1 to n. The Lagrangian multiplier, the final Lagrangian multiplier is this equation. L is equal to half w of t into w plus for I is equal to 1 to n alpha I 1 minus y subscript I wt xi plus b. This is the Lagrangian equation, and this holds good for all alpha I. Alpha I should always be greater than or equal to 0. And here we should observe that value of modulus of W square. Modulus of W square is equal to W transpose T into W. Please make a note. Modulus of W is equal to W transpose T into W. And setting the gradient of L, if we set the gradient of L with respect to W and B to 0, if we substitute the value, if we set the gradient of L with respect to W and B to 0, we will get this equation. It requires a lot of derivation here, and this is the final equation. This is the final equation, and here for non-linear separability data, here we what we do, there are some chances of errors. Here, if there is no clear separation, if data from this class enters this category, if data from this class enters this category, it means there are some errors introduced in the classification. So how the equation is written? If there are errors in the classification, the Lagrangian multiplier, this is an error term, okay? This eta, what do you say, eta? Eta is an error term. So this is the derivation. You people are in final years, so I need not go in depth for mathematics solution stepwise. Just try to solve this yourself. And this is the Lagrangian, and this is for non-linearly separable data points. And these xi xi in classification, and this is based on the output of discriminant function w of t into w. It means xi is an error term. Some samples falling from this group to this region, some samples falling from this group to this region. So some error is, if at all error is introduced, how the errors are minimized, how the prediction is done. That is done using Lagrange's multipliers. You just you study Lagrangian equation, Lagrangian multiplier more in detail by googling, okay? And here xi, this xi approximates the number of misclassified samples. errors. That's all. Xi are misclassified samples. So here this EI is error introduced from here class 1 to region. This EI error introduced from class 2 to the region. And here we have to transform Xi to a higher dimensional space. And here we come across with two terms, input space and feature space. Input space is the space where point xi are located, that is independent values. And feature space is the space of f of xi after transformation. This is input space always refers to the independent variables. Feature space refers to the output after transformation, after shifting from 2D to 3D. This we already saw, kernel functions, different types. Do you have any classes now? Please, students, please go through more in detail about Lagrangian multipliers. Okay, try to understand the concept. It is third semester. It comes in third semester. Statistics, queuing theory, probabilities. Okay, and all ML concepts are based on statistics. Statistics is not that tough. It is easy to understand. Only thing, it requires a lot of practicing. Okay, try to learn those concepts once. Okay, having said that, all of you please take care, stay safe, and bye. Am I audible, students?
Ma'am?
Yeah.
Do you like? I wanted to say something. Like, do you have time for 5 minutes? Like,
Yeah. So please go on.
yes, ma'am. You can stop the recording. Anyway, class is over.
Hello. Yeah, tell me.
Ha, ma'am. So,
You have any queries?
no, ma'am. Can you just upload the slides? Like,
Yeah,
I
I
don't think
thought of
they're
uploading only after completing, but if you want me to upload SVM slides, I can do that. Yeah,
Yes,
tomorrow
ma'am.
I'm
Yes,
done with
because
SVM.
it's getting
Yeah,
difficult to
tomorrow.
follow up with the classes.
Sorry?
Like,
Voice?
if you upload slides, then we can probably follow up classes better. Like, it's getting difficult even when we are taking down notes.
Okay, okay, fine. Today I'm done with SVM. I will upload right now. Okay?
Thank you.
Okay, fine.